All right. Hello, everyone. Welcome to today's installment of the Corundum status updates. So mainly I just have some status updates of stuff I've been working on over the past couple of weeks here. All right, so let's get into it. So not much to say on the previous couple of bugs that I've been highlighting here, but there were two other bugs that I found and fixed over the past couple of days, actually, that are worth mentioning because they probably affect some people. That I made some additions to the APIs. Basically, this is in terms of the clock info register block that was added recently, and then some of the statistics subsystem components that have been around for a while but haven't really been fully baked, if you will. So fleshing in some of the details there. And then the other thing I've been working on primarily is the AXI virtual FIFO, so I'm going to talk about that a little bit. And then I've also been doing some work on the DMA benchmark application. I forgot to add a bullet point here, but I'll talk about that a little bit in a minute. And I guess that also touches a little bit on the DRAM integration, I suppose. That's about it. The rest of the stuff is all carryover stuff. Batch completion right. I'm going to get back to working on that at some point. And then the variable length scripter management softcore and the fully integrating the 10G25D switching is all carryovers. All right. So parent PCIe hard IP core bug in terms of the back pressure. This is still to do at this point. I have the tag management implemented in the hard IP core model, but I need to update the DMA engine and make the connections to actually make that work. So at some point, I'll get back around to hammering on this. Like I said before, this only seems to pop up in combination with some of the more recent changes that I've made that haven't hit the repo yet because they aren't quite done yet. So unless somebody else is running into this, it's not super high priority to get it fixed. All right, so next up, the FIFO memory inference issue on the Intel devices. Let's see. So this is the one where there seems to be some sort of issue with how Quartus is setting up MLabs. Nothing new on my end here. My understanding is that the folks at MLE have opened an issue with Intel about this, but I have not heard anything from them in terms of updates. I just asked Joachim about that. He said he doesn't know if there's any updates. Ulrich, I don't know if you have any other information.
Yeah, so Intel is working on it. So we provided some additional data, and they will reproduce it on their end in simulation.
They were able to reproduce it?
So we were able to reproduce it, kind of putting in parallel what works for us and the original way, and that convinced them to further follow up on it, and they are creating their internal simulation for it. And I don't know if they use any public data for doing this, or if they're actually using internal data. Not sure, but yeah, they were working on it.
Yeah, it sounds like there's several potential possibilities for what's going on here. But yeah, okay, it's good that they're working on it. So hopefully we'll know. I mean, who knows when, but soon, relatively soon, hopefully, what the solution is going to be. If there's a some sort of a workaround, or if it's just, well, let's wait until we have the next version of Quartus where they fix the bug. Yeah, okay, well, that's good to know. All right, so moving on. Let's see. Recently, someone opened an issue on GitHub reporting that the NIC functionality didn't work when the DMA benchmark application was enabled. And well, that's not supposed to happen. So I took a look and reproduced the issue in hardware. And from looking at the output in MQDict dump, it indicated some sort of an interrupt issue. So, like there was stuff in all of the queues, including the event queues. So obviously, software was not noticing there was stuff in the event queues, and nothing was getting handled. So after a lot of head scratching, I finally realized that the MSIX table offsets were incorrect. And under LSPCI, you can see that very clearly. And it's like, well, okay, so if software is not setting up the MSIX interrupts correctly, then obviously interrupts are not going to work. So I traced that to it's basically something weird that happens in Vivado. If you change the bar configuration via TCL, or I guess probably also in the GUI, it blows away the MSIX settings, which is kind of annoying. Now, the way the build process works, at least with the makefile, is that it writes out a a TCL script to create the project. And that TCL script sources a few things. So it sources a TCL script to create the like the PCIe IP core with kind of a default set of board specific settings. And then later on, it sources the config.tcl script. And that one, mainly it sets a bunch of the top level Verilog parameters that propagate down into the design, but it also changes some settings on the PCIe IP core. So that those settings match. So like if you enable the application section, then it will turn on the bar. If you set the application bar size, it sets the bar size, and it also sets the parameter informing the design of what the bar size is. And then that sets the address layout and whatnot. So with the application section disabled, the bar settings didn't change and the MSIX settings didn't get touched. But if you enable the application section, then it would blow away the MSIX settings. So fix for this is relatively straightforward. I basically just kind of reorganized the config.tcl script to do the bar config first, and then go apply all the other settings. And then I went and I copied over all of the MSIX settings. So config.tcl basically just applies all of the MSIX settings. And this solves this problem. So if you're using the application section, yeah, you'll probably want to update the config.tcl to match, just to make sure that these settings get applied correctly. So this is only going to be an issue if you're also using MSIX. So if you're using some old version before MSIX was supported, then this I don't think would be a problem, because I don't think it blows away the MSI settings, only MSIX. And I'm also not sure if this is like UltraScale or UltraScale Plus specific. Like if you're on a 7 series part, it might not do this. I haven't played around with it in too much detail. But anyway, relatively simple fix in the TCL to make that work. All right. While I was debugging that, I ran the DMA benchmark application and discovered that the write bandwidth was lower than expected, around 76 gigabits per second instead of 110. Originally, I thought the issue was linked, right? Something was going on, like maybe there was an issue in the interrupt generation part of the HDL that was resulting in it generating just like a stupid amount of PCIe writes that was eating up the bandwidth and preventing interrupts from working. Turns out that wasn't the case, right? Because I fixed the other problem with the MSIX configuration, but this bug was still there. So some cycles wasted trying to figure out what could cause both of these issues at the same time. But the really weird part is that even though the DMA write bandwidth test reported 76 gigabits per second, if you run the iPerf test, it'll hit 100 gig line rate on RX. So I don't have an explanation for that. So yeah, not sure what's going on with that. And after fixing this, it didn't seem to affect the iPerf test. So yeah, that's a head scratcher. I have not figured out what is going on with that yet. But anyway, I traced the problem to the transmit limit setting for the write DMA module. And this was used very early on to prevent headline blocking issues by limiting the number of outstanding writes in the transmit path in the PCIe hard IP core. And the issue, or the whole point of this, is to make sure that you don't put more read requests or write requests in the hard IP core than it has effectively buffer space for, such that when it does run out of internal buffer space, for whatever reason, you're not getting headline blocking between reads and writes. But now that I have the credit-based flow control setup implemented, this is no longer, well, it's no longer really necessary, and it's also not very helpful, because we now have a couple of rather large FIFOs that sit in between the DMA engine and the hard IP core. So basically these limits need to be set much higher in order for things to work correctly. So what I ended up doing is just removing all of the PCIe DMA parameters settings from the top level and just falling back on the default settings, which should provide higher performance. And once I did that, lo and behold, the DMA write bandwidth test popped up to where it should be at around 110 gigabits per second. So because I didn't see an obvious change to the iPerf performance before and after making this fix, I don't know if this might be causing other problems. So if you're having weird issues with the receive performance, you might as well try it with the the latest version of the code, just to see if that helps at all. Not sure if that'll be the case, but just a bit of an FYI that has also been fixed. All right, so moving on, I also went and I added some APIs for the clock info block and for the statistics counters. And this is added both to the kernel module. So from the extension module, you can use the external calls provided by the core kernel module, and also the user space library. So you can access this stuff from user space as well. So basically for the clock side, I added some calls to read the nominal and measured clock frequencies for the core clock, the nominal for the reference clock, and then the measured frequencies for all of the additional clocks, which at this point is just the RX and TX clocks. And then I also added a couple calls to convert between cycles and nanoseconds for the core clock and reference clock. So, if you want to dial in some particular delay and you have the wall clock time you want, well, you can use the call here to get that in cycles. And this internally uses the fractional periods that are reported in the clock info register block. And then the other thing I did for the statistics counters is I added a call that lets you just specify what counter you want, the index, and it'll read the counter for you, and also figure out the correct location of the statistics counter, of the set of statistics counters. And the reason that's necessary is, well, one, it was moved when MSIX support was added, and that means it's in a slightly different spot if you're using either AXI or PCIe. And there may have been another change as well that causes that to be moved again. I think that's the main one. But yeah, basically the this resulted in the DMA benchmark application module, the extension kernel module not working correctly because it was looking for the statistics counters in the wrong spot. So with these couple of changes, I've now gone through and overhauled that module such that it's now, using the correct APIs and reading the correct locations in the correct registers. And let's see, I think I did. Oh, I also did a couple of other things. I guess in the mqnix dump code, it's now, reading all of the clock info and dumping that, and it's also reading all of the statistics counters and dumping those. There's still a few to-dos here. Main one is, I need to do a better job allocating the statistics counters. I mean, for right now, it's not really a big deal because the only counters there are, NIC level counters in terms of the PCI Express and DMA interface and whatnot. But eventually I need to add counters for, all of the Macs, potentially, PHYs as well, and all of the interfaces and, lots of other internal stuff. And there has to be some way of kind of exposing that information to the driver and to the user space tools such that you can figure out what counter does what. And then have a way of querying, based on the index, what is this counter exactly, instead of just the value. That's definitely important, but to figure out what it represents. So I don't have a solution for that yet. That's something I got to figure out, and then obviously implement some APIs to get some of that information. So you can say, instead of just having an API to get the counter value, you can also have another API that gets you a string that corresponds to the name, and then that can be connected with the ethtool API and whatnot later on, so you can get all of the counters in a nice format from ethtool. But it's not implemented yet, but there's movement in that direction. So that's that. And then for the AXI virtual FIFO, this is another thing that I've been working on over the past couple of weeks here. The AXI virtual FIFO is a component that will allow you to store packet data in DRAM at full 100 gig line rate. And the idea is to store not only the packet data itself, as well as sideband data and framing data. So some of the AXI virtual FIFO modules that I've seen, bouncing around, including, the Xilinx one. I know there was one from, the folks that make that other PCI Express core. It's drawn a blank of what it's called right now. They have a deep FIFO that they released. Zillibus, there we go. Yeah, they released a deep FIFO as well. Might be a couple of others that I'm drawing a blank on at the moment. They all seem to have limitations in terms of what can be stored. Pretty commonly, they will store just the data, right? No sideband data, no framing data, nothing else. So that makes it somewhat difficult to store packet data. So, my plan here is to implement something that AXI stream in, AXI stream out. It figures out all the details internally and recreates all of the cycles exactly on the other side. So, and the intent is to support doing that at 100 gig with all packet sizes. Now, in order to hit 100 gig, you don't have enough bandwidth on a single memory channel, so you got to use at least two. So DDR4 2400 times 2 will give you 100 gig RX and TX at the same time, or seems like 2 HBM ports, at least on the older scale plus devices at 450 megahertz. That should be enough as well. The main bottleneck here is the memory bandwidth, so I need to get a relatively efficient encoding scheme working to store both the framing and the sideband information in the memory. So I got some ideas for how to do that. I got to hammer out the details. So the status right now is that the core portion of the FIFO is working in SIM. I'm preparing a test in hardware just to make sure everything works and all the timing parameters are correct and whatnot. And the encode, decode, to store full AXI stream data is to do at this point. I want to make sure the core FIFO is working, and then I'll hammer on the encode and decode logic that sits on top of that. Yeah, so progress being made there. DRAM integration, this one I'm slowly chipping away at. I have the like I said, I added the MIGs a while ago, and also the HBM controllers, and those are connected to the application section, but I haven't done anything to test to make sure this is actually working correctly. So the plan is to use the AXI FIFO module and wire that up with like a PRBS generator and checker and test to make sure all of the memory interfaces are working. I'll have some more details on that in a minute. And then I also need to connect it up to the PCIe bar so you can access it from user space, or not from user space, from the host computer, which potentially means from either user space or kernel space. And then also the DMA subsystem connection such that the core NIC functionality can potentially access stuff in the DRAM. And then obviously I'll have options to enable and disable this stuff depending on what the application requirements are. Let's see. Yeah, so that'll be exposed through the RAM bar and the AXI port. I think I've discussed this before. Also, this will be taken care of at some point. Let's see. But that then brings me back to the DMA benchmarking application. The DMA benchmark application I've realized is kind of a useful test / sanity check in terms of making sure all of the internal interfaces are doing what they're supposed to do. Doing benchmarking with iPerf is great in terms of making sure the NIC functionality is working, but it's also useful to run kind of more fine-grained tests on the hardware just to make sure everything's doing what it's supposed to do. So what I'm planning on doing is taking the DMA benchmark application and extending it effectively to turn it into sort of, I don't really want to call it a BIST, right? Because that's a built-in self-test, but same kind of idea. You can take this and you can run it as a sanity check and basically hit all the interfaces and make sure everything is working correctly. And I can run that on, new boards just to make sure that, everything has been set up correctly. So for now, what I'm going to be doing is taking the DMA benchmark application and extending it to directly test all of the available memory channels using the AXI virtual FIFO. So take the virtual FIFO, I'll add a PRBS generator, PRBS checker effectively to, feed it. And then you can run that against all of the memory channels and make sure that they're all hitting the, expected bandwidth. And the other thing that I'm going to do is I'm going to go ahead and add the DMA benchmark application for all the target boards. So you'll be able to just go into the FPGA app, DMA benchmark, whatever, make program and make sure that that the board is working correctly. So status on this is I've refactored the DMA benchmark, the main module, to peel off the actual benchmarking components into a separate module. I've updated it to use the register blocks, which will make it a lot easier to add additional components. I've gone ahead and added it for all the Alveo boards, and the relatively short-term to-do is to add the DRAM test components and add the makefile and config.tcl for all of the other boards, such that you can build this and make sure that everything is working as expected. So hopefully that won't take too much longer. All right, I think that about rounds it out for stuff that I've been working on over the past couple of weeks here. I think the rest of this will carry over. So back completion right. Yeah, I'll get back to that relatively soon. I got all the same graphs here. I should probably remove some of these slides if it's not if there's nothing new. Very blank script support. I'll get back to that after the after I have the write back stuff working. Right. I think that about rounds it out. So we got the management software, 10G25D switching, also to do, and yeah. Okay, so that about rounds out everything that I wanted to talk about for this week in terms of everything that's new over the past couple of weeks. Does anybody have any questions or comments on this? If not, then we can open it up to discussing whatever people want to talk about. No questions or comments?
Are these back in the main tree now?
They will be soon. I'm going to do a synthesis test today. I'll kick it off a little bit later today, make sure it builds on all the boards and there isn't some like weird timing issue. And then yeah, I'll push that into the main repository
Okay.
within the next day or two.
Yeah.
But this is
so
what?
When you push it out, do you send a notification when it's updated?
Yeah. So I basically I've kind of been treating the main Corundum repository as kind of the production version. So every time I update that, I'll send a notification around to everybody. I've kind of been using the sysnet repository that we have at UCSD as kind of the main development repository for this. So if you want to take a look at these changes and try it out, you can just pull from that repository.
Okay, cool.
I'm not sure if you have the link to that. I'll get it for you real quick. Let me see. Where did I put that? Just head it up. This is what happens when you open too many tabs. Maybe I close it. I don't know. Let's see here.
While you're looking for that, I'll just throw out that we did talk about our little conversation tonight about trying to do some type of a PCIe TLP tap, adding a proxy in between other devices. So I don't know if anybody else was interested in collaborating on that.
Oh, right. You're asking about net TLP basically, and would it make sense to implement something along those lines? Either on top of Corundum or next to Corundum or something like that.
Yes, I didn't know if anybody else was interested in dabbling with that. So let's try and connect up.
Is anybody else on here heard of NetTLP? It was a paper at NSDI, a couple of years ago? I think it was from 2020.
3 years ago. Was it 2019, I think? But yeah, it was basically, I think it was a T705 and a 10 gig, and they were pulling the TLPs off and bringing them into software and copying them in Wireshark. And Just got me thinking we could be doing something similar with some of the Corundum pieces.
Yeah, I put the sysnet repository link in the chat, so you can take a look at that. Let's see. Well, I guess the other thing is you can also take a look at when you go to the repository on GitHub, you can look at the the list of all the forks, and you can look at the one that's just the newest. And that'll be the one. Let's see. Yeah, so I've kind of been using that fork of the repository as kind of my sort of stable development branch, and then my own fork I've been using as my unstable one, where I'm putting together some of the newer functionality that's not quite fully figured out yet. So just kind of FYI. Yeah, so I did take a quick look at the NetTLP paper to refresh my memory exactly what they were doing. I think it was NSDI 2020, and there were a couple of interesting notes in there. They said that they were working on the KC 705 dev board with PCIe Gen 2, and there was a note in there about not being able to access the raw TLP headers on the Gen 3 devices. So seems like they were thinking about doing this on Gen 3, because hey, if we have an ultra scale plus device, you might as well use that because it's going to be faster, right? But it seems like there was some sort of some sort of limitation there. And that's kind of the sense that I got as well, just looking at how the ultra scale plus IP cores work, because Xilinx has their, what do they call them, descriptors or something. They have their own effectively TLP header format that they provide on the interfaces. They don't give you the raw TLP headers, and there's some advantages and some disadvantages of doing that. Disadvantage obviously is it isn't the actual TLP headers. But I guess the advantage is that like the core will automatically insert its own bus number and whatnot. So you don't need to do what some other cores do, where you got to look at the bus number and then insert it. And there's something about like the addresses are always 64 bits. So you don't need to figure out, okay, is this 32 or is this 64? How many D words are in the header, yada yada yada. So, but potentially that makes doing something like NetTLP more difficult. But maybe there's kind of a restricted version that you could do with the UltraScale Plus series devices. Depends on what you're trying to accomplish.
Well, I'm working on a project with some NVMe stuff, and I was just curious about trying to get an actual tracing of all the messages as the driver is setting them up. So I'm also looking at the NVMe host app from Xilinx. But then it just got me thinking that, hey, this might be kind of neat if you've got PCIe and you've got high-speed networking. I could play around with doing this remotely across two Corundum boards with a remote site, and just looking to play a bit in the sandbox. So curious if anybody else was interested in bringing a shovel and playing with me.
Well, we did something that could be useful in this case, but it's not public. So we implemented kind of a distributed PCI Express switch, and there you're able to look at every TLP that goes through it.
Okay. And you said it is public or it's not?
Pardon me?
You said it is public or it's not?
Well, the information that we did it and partially what we did with it is public, but the actual design is not.
Okay.
But if you're interested, you could just maybe reach out to us and see if we can provide something to you that may work for you.
Okay, great. Yeah, I'll ping you on the IM then.
Great.
So you say distributed, this is across multiple FPGAs or something?
It's across a network.
Across a network.
It's running across Ethernet.
Ah, okay, I see.
So you can really distribute PCI Express devices across a long distance.
Yeah, I think one of the points in the NetTLP paper was in terms of the TLP request timeouts. So I think latency can be a significant problem for PCI Express devices. That's going to limit how far you can go.
Yes. Yeah, there are multiple timeouts in the hierarchy. But yeah, I think that the most important one in this case is the read request completion timeout, right?
Right. Yeah, definitely. Yeah, and I guess the other issue that you run into as well is just the number of outstanding read requests that you can have at any given time. That's going to be determined, by how many tags you have available. And if you have a big delay, then that's going to affect your DMA throughput. So, but for applications where you don't care too much about that, and having a long fiber or whatever between the host machine and the the destination device, where that's advantageous, then that might be a reasonable trade-off. Yeah, the other thing that I have lying around that's interesting from a PCI Express standpoint, potentially, I haven't done anything with this yet, but I have one of the Stratix 10 MX dev kits. And the fun part about this is it's got not only PCI Express edge connector here for a host, but it also has a slot for a device. So I was almost thinking, you could take this and basically turn it into a PCIe protocol analyzer, right? You could just pass the traffic straight through and then tee it out onto the network if you wanted. Or you could even just totally split it, right? You could take the traffic here, send it out here through your switch or whatever, come back in. And there's a bunch of stuff you could potentially do. Since I already have one of these, maybe.
So you need my shipping address? Is that what you're saying?
I don't know. Maybe you can ask Intel. Maybe they have some extra ones.
You could also use a Zinc MP based Sidewinder board that also has these two interfaces. If you have one.
Yeah, I don't have one of those. I was talking to the people at IBM a while ago who were looking at doing something with Corundum, and they have one of those. Which one?
Sir, can you write the name of these boards on chat? I want to.
I'll do you one better. I'll give you a link to it.
Okay, and also the one with Zinc. Can you give me the name, Jochen?
Oh. Yeah, Sidewinder.
I will give you both links.
Yeah. Yes, it would be good. Yeah.
Fidus Sidewinder is the first one. Well, all right, the second one. That's the Sidewinder. And then the Stratix 10 MX dev kit. Let me see here. Oh, I'm just looking at the FPGA dev kit. Come on, there we go. All right, there's a dev kit. Yeah, and the Stratix 10 MX ones are the ones with the HBM. So I think, the card that they sent me has the 16 gigs of HBM, but I think they have a 16 gig version and an 8 gig version. It's just a different FPGA part number that's on there. So yeah, there you go. They are, well, the boards are nice. The FPGAs, slightly different story. They're not the fastest. The Agilix ones are definitely a lot faster. Yeah, okay. Did you get those? Oh, there we go. Adam John got the links. Cool. Let's see. What else? Oh, I guess I can also pop the NetTLP link in the chat real quick because I have that up. Here we go. For anybody that's interested. That's the NetTLP thing. And they have they actually have a whole GitHub repository as well and their own little site. So anybody else interested in that, there is the site. And then the GitHub repository, which is linked from the site, but yeah. So did they make their FPGA code available? They must have. Oh, that's one of the repositories, but they have several on that GitHub org. They also have a modified version of Wireshark, which will decode the PCIe TLPs. which is pretty cool. Yeah. Anyway, oh, so they do have their adapter code, FPGA based NetTLP adapter.
Yeah, I did the KC705 out of the back room, so.
Right.
maybe I'll
Yeah.
fire that.
Yeah. So they have the code. You might as well give it a shot, see if it works. Yeah, I guess with that one you're limited to, I think it was Gen 2x4, was it? Not very much bandwidth. And then the 10 gig link. So, but you can at least try it and see how it works.
Yeah, well, give it a shot.
All right. So let's see what else. Anyone else have anything that they want to discuss? Any other questions or comments, or should we? I don't know if we need to turn it over to MLE at some point. Hello, Bob.
Alex, hey, how you doing? Quick question regarding PTP and the
Okay.
implementation. I think 96 bits, right, is what I saw that
Yeah,
you have 96-bit.
that's the standard PTP timestamps. I think
Yeah.
is 96 bits. Yeah,
Right.
they have a 64-bit format and a 96-bit format. The 64-bit
Right.
ones are like relative timestamps.
I just wanted to get some background. You used it in you've used it with PTP4L, right? And you've implemented the adjusting the clock and then let PTP discipline the clock. And do you
Right.
think, and you've hooked it up also, if available on the to a temperature control or the best oscillator on the particular NIC? Is that what you try to do? Or do
So
you just-
let's see. Initially, I hooked it up to the PCI Express oscillator, basically,
Okay.
but I changed that relatively recently. So right now, it uses a separate reference oscillator for the PTP hardware clock. And I guess in principle, you could wire that up to whatever you want, but I've just been connecting that up to the Ethernet transmit clock. And the idea being on quite a few boards, that'll be sourced from a PLL chip that supports, fractional operation with the PPB kind of resolution. So you could potentially use that for like Synchy, White Rabbit type stuff. There was a bit of a discussion on GitHub a while ago about potentially implementing White Rabbit on Corundum, which can potentially time sync down kind of into the picosecond range.
Right.
And I think it would be possible to do that on quite a few boards. So in this case, it's not so much about the stability of the oscillator on the board. It's about the ability to, use the Ethernet transmit clock for the PTP clock, and then be able to slew that on, PPB levels. So, we'll have to loop in a softcore to actually do the slewing in the time sync. But
okay. But that's only for White Rabbit, right? If you're not doing White Rabbit, you want to hook up the best oscillator on.
Well, so on most boards, the Ethernet transmit clock is the best oscillator that's available anyway. So yeah. I mean, that might not universally be the case, but on most of the boards that I've looked at, most of the Xilinx dev boards, they just give you a bunch of the SI 570s or whatever. So, they're all the same. If you're using the PCA clock, then you're getting whatever's coming from the host, and who knows about that. Right. That's going to be off by a lot, but yeah.
Okay.
Some boards obviously give you something better.
Yeah, we do on some of ours. We have a better clock. We have an HPT and goes down to Pico 7. We have ones that are temperature controlled on all our boards. It's a 10 megahertz. And I was like, well, maybe I want to try using that with
but yeah, so you should be able to do that with Corundum without too much difficulty. It's just by default, everything is set up to use the Ethernet transmit clock just to support, those type of applications. And because that's the only oscillator that you're guaranteed to have available basically on a given board, right? Now there are some gotchas that I've run into so far with that. Like I think on some of the like Intel Agilex parts, they don't necessarily give you like a clean reference clock output from the Ethernet PHY layer components. The only way you can get is like the user clock, and the problem with that is that like if you reset the core or reconfigure it or something to run at a different rate, then that clock gets interrupted. So that's not ideal. I haven't been able to figure out if there's any kind of workaround for that, but I'm assuming they just don't have enough pins in the EMIB to give you just a reference clock straight across. On some of the other devices, you do get that. So like on the Stratix 10 non-DX, you can get the reference clock directly from the serializers. So that works great. One thing I did notice, because like on your point, you want to use the highest stability oscillator you can get away with. They have some super high stability oscillator on the DE10 Agilex. So I need to take a look at the exact specs on here, but they have a pretty beefy oscillator here, which is some oddball frequency. It's like 30 some odd megahertz. But it's supposed to be super high stability. I think it's actually like an oven compensated oscillator on there. So I don't know.
Yeah, that's
how
what we
much
have.
power it consumes, but yeah, it's not a TCXO, it's actually an OCXO.
Oh yeah, it's an OCX. Yeah, we don't have that.
Yeah.
Rubidium is the next step up, right? We don't have that.
Right, yeah. You know, you're moving up the size and the price levels as you go to the higher stability. But yeah, on that one, I'm like, it's a relatively large can, but apparently that is I don't know if you can see that, right? It looks like just kind of a standard you know, kind of through hole oscillator. That's kind of the size of that, but it's apparently an OCXO. I'm like, well, okay, that's interesting.
Okay.
I'll see if I can figure out what the part number is on that. The documentation wasn't super clear. I'm also not clear. I'm not 100% clear if that's on all of the production cards, because they gave me a like a Rev B, I think, and the production is a Rev C. So it's possible the production cards don't actually have that chip installed. So I'm like, well, if the production cards don't have it, then I probably shouldn't use it.
Okay.
But yeah, the point is that you can in principle point the PTP reference clock at whatever clock you want. You just have to set, there's a couple of parameters to determine that reference clock frequency, such that the nominal period for the PTP clock is set correctly, and whatnot. So yeah, you can point that input at whatever you want, and then you can just set the appropriate parameters, and then it'll work. So
okay, I'll take a look at it. Thank you.
yeah. Well, which boards are we talking about here? The X25 and X100, or are we talking about different?
But also,
okay,
I was looking at it for, even though you don't have it yet, the V9P, which
right,
is a bigger, is a VU9P in it.
Right, yeah.
And we also, it's a similar oscillator we have on those, and so.
Right. Okay, then I guess those would be, you said TCXOs, so better than a standard oscillator because it's got some sort of internal temperature compensation stuff.
Right.
Okay. Yeah, I guess on those, you don't have control over the main oscillator, right? It's just kind of doing its thing. It's not yeah. So yeah, on those we could definitely just change the upstream design to support the TCXO. And use that for the PTP reference instead of using the the reference oscillator for Ethernet on the boards that have those by default. It just I when I went through and implemented that for everything, I just used a transmit clock because I knew all the boards would have that, because it wouldn't be able to do Ethernet if it didn't have that.
Yeah,
and then we can go back and revisit some of the other boards and clean stuff up. So if it makes sense to use a different oscillator on this board or the other board, we can do that. It's not a big deal.
Okay.
So
yeah, it's not an urgent thing, right? I just was checking for some other, we have another application.
Yeah, sure.
Trying to use it.
Well, I'm certainly open to making sure we're using the most optimal oscillator or whatever on each board. So if it makes sense to go make a couple of tweaks to these guys so it's you get a little bit better stability, then we could do that. So
okay.
The other thing I think I noticed that the oscillators that are on there, they're like 10 megahertz or something for the
Yes.
TCXO. So
Yeah, ours, yeah.
I'm not sure
the
if it makes
ones
sense to use that directly or to multiply it up to something a little bit higher frequency with
that's
one of
what
the
we
internal
do, right?
MMCMs.
In our code, we put it at 250
Right.
megahertz.
Okay.
Yeah, and then, every 4 nanoseconds.
Right. Yeah. Yeah.
4 nanoseconds on most of our NICs. We have one that's faster and it has a better clock on it, an HPT NIC it's called. I don't know the specs on that. It might even be an oven controlled, but yeah. So the standard in our is 4 nanosecond like resolution, 250 megahertz.
Right. Well, I mean, the nice thing with Corundum is that there's parameters you can use to basically inform the design what the clock frequency is, and then those are exposed to user space. So I
saw that.
The available space and the registers are like 16 bits for the numerator, 16 bits for the numerator, 16 bits for the denominator. So as long as the frequency isn't some really weird oddball thing, you should be able to represent it, and then it will compute exactly all of the necessary values and whatnot internally for that. So
Okay. Do you know if anyone's done any tests with any boards, like high precision tests on any of this, like to see the accuracy or anything like that?
I mean, I'm not aware of anybody doing any formal tests. I know with PTP, you're not going to be able to do better than a few nanoseconds because even though internally it uses 96-bit timestamps, it doesn't report the fractional portion all the way up to user space. So it cuts it off at the whole numbers of nanoseconds. And I think the API going through user space only supports units of nanoseconds anyway.
Right.
So
Yeah.
if you don't have that resolution, then you're not going to be able to time sync any better than that.
Yeah, we have some custom code for our HPT NIC, which
right, yeah. So yeah, if you're using the kernel stack, at least I think that's kind of a limitation on what you can do. If you're doing something customized, either closing the loop in the hardware or closing the loop with custom user space software, then you could definitely do better than that. And at some point I am going to change the the completion format a little bit, and in doing that I could potentially add some more bits. Well, I guess the other aspect is that the Xilinx 100 gig max, the CMax, they only report 80-bit timestamps, so they don't report the fractional bits at all, which is kind of weird, but it is what it is. So yeah, for everything with 100 gig, you would have all the 16 LSBs at zeros, which is not great.
Yeah.
Guess the other thing I should mention is that I'm not sure necessarily if my PTP CDC logic is 100% perfect. So obviously it's good enough to time sync down to within microsecond level, but if you're getting down to individual nanoseconds, it's possible they need some work to improve the performance a bit. Not sure about that. I mean, like I know Intel had some code, and I was looking at the documentation for that to try to figure out what the proper technique is, but I might not have done it the best way. So
I appreciate it though.
If you guys have any comments on that to improve it, I might be all ears.
Okay, all right. When we start looking at it, yeah, thank you. That's all I had. Thanks.
Cool, thanks. All right, does anybody else have any questions or comments? Anything new from MLE's end? I guess the most important thing is that that bug has been handed off to Intel and they're working on it, so that's good. Nope.
Yeah, fair assessment, I would say. So as I said before, no news from my side.
All right.
So I don't know if Ulrich has any topic.
No, not really. I think everything's so going on.
Yeah, sounds about right.
Yeah, at
All
some
right.
point, I think we already announced it at some point in the past, but we didn't really get to it to kind of push something yet. So we did some work on implementing some automation on doing birds and eye scan on the Stratix 10 devices. So we are just now using it productively for bring up testing. So this is a standalone thing based on XFCP.
Okay.
Running some 100 lines of code of Python. Yeah, so that works. And at some point we want to push this, but yeah, we need to do another round of cleanup and possibly refactoring to make this in a little bit better way.
Yeah, sometimes it takes a few iterations to come up with the best solution. Like first pass, like just get it freaking working. And then once it's
Right.
working, then you realize, well, that was a really stupid solution. We could do it this way and it'd be 10 times better. So yeah, usually that's what I factor whenever I'm going to build something non-trivial. It's got to be at least a second or third iteration that's actually going to be the good one.
Exactly. So we have something that works, and we get some test logs out of it, so that's good. But yeah, it's not nice. So I guess it needs another run through it. Yeah, but other than that, I think yeah, we're still working also on interfacing the SDM mailboxing IP.
Yeah, that's important. Yeah.
I
And
think we got another.
this is just for firmware updates or for a few other things as well. I guess maybe also monitoring.
Yeah, right. So the plan is that at some point there will be another little user space tool that can interact with the SDM. And we could also use it to monitor voltage and temperatures, for example. So that would be interesting, I guess.
Yeah, I guess the Intel equivalent of the x86, I think, is that access through the SDM?
Right.
Okay.
And yeah, I guess that's the interesting monitoring part. And yeah, firmware updates obviously is also an interesting aspect of it.
Yeah, okay. Actually, what I'm going to do right now is open up a, well, or get ready to open up an issue on GitHub here to discuss the firmware update format, because I think that would be useful to kind of come up with something standard that'll work for both Xilinx and Intel devices. I was putting a little thought into that actually over the past couple of days. Just it would make sense to have just a zip file plus a manifest file that has information about what the firmware revision is and whatnot, as well as instructions for what needs to be done to update the firmware in various partitions. And then you can just put the programming files directly in there, the bit file, the POF file, whatever. And you can potentially even put some additional supporting files as well. Like I know the Xilinx tools, they'll write out an LTX file with debug probe information. It'll write that out even if you just have MIGs in the design. So including that could make sense. Potentially even some log files, timing report. Hey, yeah, this one actually did close timing. Stuff that might be useful to look at later. You could just toss in there.
We did some extensions to your make file to actually check for timing issues, both for Xilinx and Quartus builds. That's also something we need to find time to open a pull request for.
Oh,
so,
okay. Yeah.
And in addition, we also generate, at least for our case, the Flash files that are used by Quartus programmer, the jig files, also via the make file. So that there are some additions that are nice to have, but yeah, not necessarily required to get a bit stream and program it manually. Right. But yeah, we are building this into our CI, and that then in the end spills out all these artifacts. It actually also, there is another makefile target for creating archives of all of these projects, both for the Xilinx and the Kratos builds, so that you have like, what did we do, or what did we have in place when we built this? Yeah, some small items, but at some point, I guess we want to give them back, but we need time for this.
Yeah, well, all in due time, you know, we can get everything all sorted out. Yeah, that sounds pretty good. Yeah, so I'm going to go ahead and open up a GitHub issue that we can use for discussion in terms of you know, what the firmware format might look like. Because I've got some ideas for what needs to go in there, but I don't have a complete picture, especially in terms of what needs to be done on the Intel devices, because I know they have a more complicated format for the flash on there. So when you're updating something, or when you're just doing an initial, you know, burn of the flash, you know, what needs to be done for the various partitions and whatnot. You know, I think we'll have to come up with some sort of a method for describing that the firmware update utilities can then understand.
Yeah, yes, and there is even more information in that. So especially for the StratX 10s, there is also the SDM firmware being part of this soft block. So this is a little bit strange. So there is more information in there than quote unquote just the bit stream.
Right. Yeah. Yeah. For the Xilinx ones, it's just like bitstream, boom, done. But for the Intel one, I remember looking at one of the boards and there was like, I don't know, 6 or 8 different flash partitions or something like that. And you got to write different stuff into each. I'm like, what the heck are they doing? But yeah, so obviously it's not as simple as just you specify one programming file and you're done. So, you know, what sort of, so if we're going to do something like that in if we're going to support that kind of a setup with the firmware update tool, you know, there needs to be kind of a standardized way of describing, you know, what needs to go where when you're doing various updates, right? Because for some, if you want to do like an initial flash from just a blank flash on there, then, you know, you have to do certain things, and you have to write basically all of the partitions, presumably. Versus if you're just updating the firmware, maybe you just need to update a couple of the partitions. So whatever we do, it's got to be flexible enough to support, you know, that sort of thing. And then presumably it would also work just fine for the Xilinx ones, because it's just, hey, just write this one partition, you're done. So, oh well.
Yep, that's quite some items to sort out for this topic.
Oh, I guess another thing that I'm not sure if I mentioned this before, but from some of the code that Bitware provided, they have bits and pieces of code to read the POF file format from Intel, and basically extract the bit file from that and avoid having to generate an RBF through Quartus. You still have to generate the POF, but you can directly interpret that. So I can potentially, I think I wrote some Python code that basically does the same thing. So if you guys are working on that, I can post that somewhere because that might make the process a little bit easier for generating everything. Yeah, maybe not. I don't know. POF versus RBF, maybe similar level of complexity to generate both of them.
Yeah, I guess. Yeah, let's have this discussion again when we are getting closer to actually working on this. Yeah.
Right. Yeah, the only reason I mentioned that is that the Xilinx bit file format, it is kind of documented a couple places, but I have not found any documentation for the POF file format anywhere. So I'm not sure if that you know, Bitware's code was put together based on documentation from Intel, or if they reverse engineered it, or what. But yeah. Anyway, is there anything else to discuss? I think we've about covered everything, so. All right, well, if that's everything, then I guess we'll go ahead and adjourn for today. And 2 weeks will be the 19th. Bob, did you want to say something?
No,
Okay.
goodbye, thank you. though.
Okay, I saw you come off of mute. I wasn't sure if you just wanted to say
Just
bye or if you
saying,
had something to add, so.
No,
All right,
No.
well, I guess we'll adjourn for today. We'll see everybody on the 19th in 2 weeks. Cool, thanks everybody
Good.
for tuning in.
Thank you.
Yeah,
Have a
like-
nice 2 weeks.
Bye. Bye. Thanks.
All right, see ya.
Thanks. Bye.